So let's consider the series sum n from 1 to infinity of 1 over n squared. And I'm going to ask a question for this series that we're going to ask throughout the remainder of the next, at least the next few sections of the book, but really we're going to be concerned with this question for the remainder of Calculus 2. And that is, do we think that this series, or can we show that this series is convergent or divergent? And remember that a series is convergent if its sum, if the total sum is equal to a finite number. So if we can add up all the infinitely many terms of this series and get a finite number, then we say that the series is convergent. And otherwise it's divergent. And series can be divergent for a number of different reasons. Of course, if the series is convergent, we're then going to want to ask, okay, well, what is the sum? So what does it actually add up to? For right now, though, let's just focus on the question of, is it convergent? Does it converge? And for this series, what we can do, this is not the most complicated series here, at least the 1 over n squared is not the most complicated. So what we can do is we can replace the terms in the series, sometimes called a summand, the 1 over n squared. We can replace this by a function, and we can plot the function 1 over x squared. So I've drawn here a set of axes, xy axes. And we can replace this series, like I said. Remember, we can think of a series, or a sequence at least, as a function whose domain is just integers. But let's replace this by the continuous function f of x equals 1 over x squared, defined on the positive portion of the x-axis. So defined for x greater than 0. And then let's think about how this series is related to this function. And like I said, as we know, this sequence, at least 1 over n squared, just takes in integer values, so 1, 2, 3, 4, etc., and so it just picks out these points along this curve. Okay, and so we could call this a sub n equals 1 over n squared. That's the collection of the blue dots here. And if we want to add up the series here, what we can do is we can think about this as an area problem. So each of these points we can think of as the corner of a box, okay, corner of a box whose base is on the x-axis and whose height is determined by the right endpoint here. Okay, and we can then look at this and we can shade in these boxes and we can try to add up the area of these boxes. So the next box will look something like this. Try to make it look right. And this continues on forever, right? We want to add up these infinitely many areas. But when we look at the areas of these boxes, we notice that the base of each one of the boxes, the base is equal to just 1, right? And the height of each one of these boxes, the height here, is the 1 over n squared. And so then we can now see that the area of each of these boxes is exactly what we're looking for, right? The area of each box is then base 1 times height, 1 over n squared. Okay, and so I'm going to go to a new page here to write down what we've just learned. But what we've got then is that the sum from 1 to infinity of 1 over n squared, this is equal to the sum of the areas of the rectangles in the picture that we drew. Okay, so this is geometrically what we're trying to compute. Let's go back to the picture. Notice that in this picture, if we start at this kind of orange vertical line that I've drawn, the curve that sits above here, the curve that we've drawn is always above the boxes, right? And the area underneath the curve is always going to have this little extra portion here. And as we move out the curve, at least the way I've drawn it, it looks like that portion is getting smaller and smaller and smaller. But that extra portion right there means that the area underneath the curve itself, the continuous curve f of x equals 1 over x squared, the area underneath that curve is larger than the sum of the areas of our rectangles, which is what we're trying to compute. The only problem is that we need to kind of cut it right here, right? Because over here, this area, we don't know what's happening here, but this area looks like it's going off to infinity. But again, we're not too concerned with that because we know exactly what our rectangle looks like on this first interval here, this first portion. Okay? And of course, the area underneath the curve, that's just an integral, right? That's an integral. We can write that down and actually compute it. And so what we have then is that our sum, n equals 1 to infinity, 1 over n squared. This is going to be less than or equal to the area of the first box. By the way, the height, this is when n equals 1, right? So the height of this box is 1. So it's 1 plus the sum of the, plus the area underneath the rest of it, right? We're trying to bound this by the integral. So it's less than or equal to 1 plus the area underneath that curve. All right, and that, again, that curve is now, the area underneath the curve is the integral from 1 to infinity of this function here. So the integral from 1 to infinity, 1 over n squared, x squared, we have to use the function, 1 over x squared dx. Okay, and now our question has been changed, right? So we want to know, does the series converge? Well, the series, by the way, this is an area, sum of areas, right? So just geometrically, it's a non-negative answer. We're adding up positive areas. And it's got to be greater than 0 then, and less than this value. And so the question now is, can we compute this integral? And of course, we've studied improper integrals already, and so this is just an improper integral. So we know that to compute this integral, 1 to infinity, 1 over x squared dx, we replace the infinite limit by a limit, say t approaches infinity, 1 to t, 1 over x squared dx, and then we just compute the integral as usual. And so the integrand becomes negative 1 over x. We plug in 1 and t. And as we work this out, we now need to compute the limit t approaches infinity of, this becomes 1 minus 1 over t. And as t approaches infinity, 1 over t approaches 0. So this limit is 1. All right, and so what we've actually found, we've got a lot of information here. Number one, this integral converges. So that means that the area underneath the red curve is finite. Okay, and if we built our boxes this way, and we interpreted our series this way, then, of course, that means that the sum of the areas of the boxes must be finite. And not only is it finite, but this portion is less than 1. We have another 1 here, right? And so the sum of these two together is 2. And so that means that our sum, n equals 1 to infinity, of 1 over n squared is it's obviously positive, but it's less than or equal to 2, and it's just based on the picture, it's certainly going to be less than 2. But we still don't know what it equals, right? But we now know that it's less than 2.